Hello, everyone, and welcome to today's webinar, where we will be discussing streamlining fatty acid analysis with IR. My name is Jennifer Caveney, and I will be facilitating today's presentation. Before we begin, just a reminder that this webinar is being recorded, and the recording will be sent out following today's discussion. If you do have questions, we encourage you to enter those questions into the questions box, and we will do our best to answer following the discussion. All right, let's go ahead and get started. I have the pleasure of introducing our speaker today. Anthony Lai is the Vice President of Product and Market Development at Eurofins QTA, driving innovation in infrared spectroscopy and market growth across food, feed, and supplement sectors. Since 2013, he's held key commercial and technical roles, blending strategy with customer-focused solutions. He holds a degree from Hiram College and is based in Fort Mitchell, Kentucky. Anthony, I'll hand it over to you.
Thanks, Jen. Good morning, good afternoon, good evening, depending on where you're joining us from. Appreciate you joining today's webinar. As Jen said, my name is Anthony Lai. I'm the Vice President of Product and Market Development at Eurofins QTA. My role with Eurofins is really centered on creating testing solutions for areas of need where we leverage infrared spectroscopy. I'll be guiding us through today's session, where we'll explore how infrared spectroscopy can complement traditional gas chromatography, and in many cases, streamline your quality program's approach to fatty acid analysis. So here's what we'll cover today. First, I'll introduce a little bit of information about Eurofins QTA and the services we provide to give some context as to why we're talking about IR spectroscopy. We'll discuss why fatty acid profiling matters, both globally and within the industry. We'll walk through traditional GC approach, including its strengths and limitations. And then I'll introduce IR spectroscopy as a valuable alternative to GC testing alone. We'll compare the two methods kind of head to head, looking at cost, sustainability, and performance. Also share a real-world case study from one of our client labs. And finally, we'll wrap up with some questions and answers at the conclusion. So why are we giving a talk about the value of IR spectroscopy? At Eurofins QTA, we offer inclusive services for infrared testing. Our support spans from project initiation all the way through ongoing production. We provide all the support a company would need to bring IR testing into their in-house quality program. We have a dedicated team of specialists, including our PhD chemists, with expertise in chemistry, engineering, chemometrics, and spectroscopy. This team provides ongoing calibration and model maintenance, instrument and hardware support, data management, and 24/7 technical support. In short, we don't just sell spectrometers, but we offer a service solution that provides our customers with the support that's needed to get the value out of an IR program. Okay, so before diving into IR, let's kind of set the stage with a quick overview of fatty acids and the traditional GC approach that's used to analyze them. Fatty acid profiling is critical from both a quality and regulatory standpoint. From a health perspective, fatty acid composition influences cardiovascular health, obesity risk, and inflammation. Accurate analysis of fatty acid concentrations is vital to producers of nutritional supplements and pharmaceutical products. From a regulatory standpoint, accurate labeling of saturated fat, trans fat, and omega-3 content is mandatory for both domestic and international production. There's also an environmental dimension. Fatty acid profiling also supports traceability, helping to verify sustainable sourcing, and it allows us to assess its ecological footprint. Industry drivers make profiling equally critical. It helps detect adulteration and fraud, For example, when high-value oils like fish oil and olive oil are substituted or adulterated with cheap alternative oils. It supports research and product development, enabling innovation in healthier formulations, such as low trans, high omega-3 products. It plays a role in agriculture and breeding, guiding the selection of crops or livestock for desired fatty acid profiles. And in feed and food quality control, profiling ensures consistency, purity, and even helps predict shelf life, since oils with higher polyunsaturated fatty acid content are more prone to oxidation. Now let's look at the traditional GC approach. The workflow and sample preparation can be complex and difficult to execute at the speed needed for production. Fatty acids must be first derivatized into methyl esters using reagents like methanol and sulfuric acid. This involves multiple steps: extraction, the addition of antioxidants, methylation, phase separation and cleanup, and finally injection. The preparation alone can take 30 to 60 minutes per batch before analysis even begins. And the analysis itself, typical GC run for fatty acid profiling, takes anywhere from 15 to 60 minutes per sample, depending on what type of column is being used and the type of separation and resolution you're looking to achieve. Throughput can be limited, making it more challenging to process larger numbers of samples efficiently. GC also comes with significant consumable and operational costs. Specialized capillary columns are expensive and must be replaced periodically. Carrier gases like helium or hydrogen add cost, and with helium being a non-renewable resource, supply shortages raise sustainability concerns. Solvents such as hexane and methanol are required for sample prep, and their disposal adds both cost and environmental impact. On top of that, GC requires skilled analysts for calibration, troubleshooting, maintenance, and operation. The complexity of preparation simply increases the risk for error. However, accuracy, precision, and resolution are where GC really shines. It provides high resolution for individual fatty acids, including minor components like polyunsaturated fatty acids and trans fats. For this reason, GC remains the gold standard reference method for official compliance testing. But there are trade-offs. GC generates chemical waste from solvents and reagents, and its ovens and detectors consume significant power during those long runs. So while GC is accurate, it's also resource intensive. Now that we've covered an overview of strengths and limitations related to traditional gas chromatography for fatty acid testing, let's talk about IR spectroscopy. But before we dive into the operational strengths of IR, let's quickly review the principles behind this spectroscopic method. Infrared spectroscopy is a non-destructive test method that uses an infrared signal to help us measure bond excitation. That excitation is then measured through energy loss across a range of wave numbers and plotted to create our IR spectra. As material composition changes or component concentrations change, so will the spectra across a number of wave numbers. This graphic shows the portion of the light spectra being used. We most commonly use either near IR or mid IR. Both near and mid IR ranges have their own strengths and limitations. Mid IR is powerful because it gives us very peaky spectra, which can help visually isolate absorbance. That is why mid IR is such a good tool for spectral fingerprint analysis. However, your depth of sample penetration is very shallow, reaching only a few microns into the material. This requires a completely homogeneous sample. Near IR, on the other hand, has a much deeper sample penetration. However, the resulting spectra are over a wider wave number range and produce more sweeping spectral features. While this provides a great tool for solids, slurries, and any heterogeneous material, you lose some of the peak separation that you find in the mid-IR spectra. This illustration kind of shows us the mechanics for IR analysis. You'll notice there's no sample prep, and we're simply exposing the sample material to our IR signal. Here you can see examples of both mid-IR and near-IR spectra, as well as the difference in the wave number range along the x-axis of both of those plots. These spectra are then matched to wet chemistry or GC analysis results for the same sample and are the foundation for building the chemometric models. These models are used to analyze your test spectra and quantify results for your individual fatty acid concentrations. With that said, IR spectroscopy can be delivered through a number of platform designs. There's traditional benchtop mid-IR and near-IR spectrometers, which most people are familiar with. We also have portable handheld spectrometers for field applications or for the receiving of raw materials. However, at the other end of the hardware spectrum, we have inline units that use probes or emission heads. These systems offer the ability to have continuous monitoring of material as it moves through the process. The analysis can take place over a belt for solids, or in a pipe, or in a vessel for liquids. This creates a variety of different automation opportunities. One of the most obvious advantages of IR spectroscopy is the speed of the analysis. Spectral acquisition and quantification can all happen in under 60 seconds. This comparison is looking at the difference between near IR analysis for moisture and traditional oven method for loss on drying. With the use of IR spectroscopy and validated chemometric models, you have results in less than a minute versus the hours required to complete an oven method. This difference can instantly improve response times and allow your production teams to make variable changes in real time versus retroactively or after the fact when material needs to be reworked. Here's another illustration of how a mid-IR spectra will change based on the compositional differences between various marine oils. You can see that these differences occur across a number of wave number ranges throughout the spectra. But this is one way that IR analysis is used to verify consistency of product and flag potential adulteration or quality concerns. This table highlights some key characteristics for both chromatography methods and IR spectroscopy. When the full picture is taken in, what you find are two methods that, while different in many ways, complement each other through the lens of a quality program. Chromatography is the gold standard method and will continue to be. It provides a high level of accuracy and precision needed for regulatory and compliance purposes. However, that accuracy and precision comes at the cost of required technical expertise, consumables, solvents, reagents, as well as lengthy turnaround times. This is what makes IR spectroscopy such a great complement on the production side. It's fast, accurate, and very easy to run. Once the models are in place, the actual process of running a test can be performed by production staff and those without traditional laboratory experience. IR spectrometers are rugged and require no chemical reagents or consumables. They do not need to be confined to a lab and can be placed out in production areas where rapid quality data is most needed. So the speed and ease of use of an IR system has its own limitations. IR spectroscopy is very material matrix dependent. So any product or material changes need to be validated into the model to ensure their accuracy. Certain parameters such as polyunsaturated fatty acids and trans fats, as well as low concentration components, need more robust calibrations for accurate predictions. Since IR is a secondary method built on the back of traditional wet chemistry like chromatography, it's not a likely candidate to be an accepted method for regulatory or compliance purposes. However, it presents an excellent method for in-process, in-house work, making your GC test confirmatory. Model calibrations are advisable on a regular frequency, however, especially needed if you have any change in material composition, process, or a change in labs providing your GC results. All right, let's shift focus to infrared spectroscopy and model development for fatty acid analysis. So scientific validation of the performance of these models is critical. IR spectroscopy relies on chemometric techniques like partial least squares regression to predict fatty acid composition. Studies report R squared values up to 0.94 for saturated fatty acids and 0.91 for unsaturated fatty acids, showing strong correlation with GC reference methods. IR performs exceptionally well for bulk groups, saturated, monounsaturated, polyunsaturated fatty acids in things like dairy, fish oils, and edible oils. Prediction errors are typically within plus or minus 1 to 2% of GC results when calibration sets are well developed. That said, minor components like trans fats and polyunsaturated fatty acid isomers require extensive calibration data sets, and GC will remain the reference method for that testing. The following slides are some examples of correlation plots illustrating models that we have developed. Here in the beginning, you can see some big ones. You have EPA, and you can see our performance, our R square at 99.9, pretty wide range with an uncertainty of 5. Same with DHA, very strong R squared, small uncertainty. Omega-3s, again, 99.9 R square. FFA, palmitic, palmitoleic, stearic, all holding high R squares and low uncertainties. Our oleic acid, linoleic, and alpha linoleic. Here we have a general cost comparison between GC and IR. The highlight of this comparison is the lack of operational, maintenance, or consumables costs related to IR spectroscopy. They are a robust workhorse platforms that perform very well in production environments. This allows producers to reduce the workload and degradation of their GCs and GC columns and preserve its use for where GC's accuracy and precision are required and matter most. So we have a quick case study that we wanted to share. This case study outlines the situation of one of our fish oil clients who's looking at EPA and DHA in their product. So our client is a global leader in the fish oil industry, and they're currently processing around 5,000 tons of crude fish oil annually. Their quality lab runs 24/7, and previously they were running over 850 GC samples per month, primarily for EPA and DHA. In order to keep up with the sample rate, they had to purchase multiple GC systems and maintain them. Turnaround time on the results was less than ideal, just due to sample prep and longer analysis times. Increasing operational costs of the GCs was also a growing concern for them. However, their main pain point was the cost of their downtime, which they were estimating in up to $100,000 per day. So looking at the results of the addition of IR to their quality program, we can see significant reductions in both turnaround time, operational costs, consumables, and waste, all without sacrificing the accuracy that they need to run their production facility. So that concludes the informational portion of today's webinar. I again want to thank everybody who logged in. My intention here was to provide an introduction into how IR spectroscopy can really complement GC testing. The goal being to create a comprehensive quality approach that provides rapid testing needed to monitor production without sacrificing the accuracy and the precision and the resolution needed in the analysis of fatty acid profiles.
All right, perfect. Well, thank you so much, Anthony. Really great presentation. We do have a few questions in the chat. I think we have a few minutes here. So our first question, what potential does inline IR hold for real-time process control?
Sure. Yeah, the inline systems, they provide a continuous feed of quality data. And that's most often directed into a control room or into or through a database as a historian. Most inline users are acquiring a data point every 1 to 2 minutes, and they're creating pretty high resolution trends of their critical quality parameters. In this case, EPA and DHA. However, there are others who are taking it a step further and also looking at other oil quality traits like peroxide and anisodine value. These continuous trend charts are great for operators for what they need for monitoring their production, but others are going and taking it to tying it into their automated systems. So their automated systems will actually use near IR results to automatically control a wide number of production variables. So I would say for real-time process control, there's layers to it, and it can either be immediate data that a human operator can then use to make their adjustments, or it's something that you could tie that data stream directly into an automated controller to automatically make those adjustments in real time.
Perfect. Another question, how do you determine when IR can be used versus fatty acid analysis by GC?
Yeah. And we've mentioned it a few times, in the presentation, that the GC is the gold standard method, and for good reason. It's highly accurate and precise when your sample prep and method are well executed. It's going to be a requirement for any regulatory or compliance test, but there's a wide range of samples that get pulled throughout the production process that are perfect for IR. Any in-process sample that requires either a quick turnaround time so production can make a variable change, or to move that material on to the next stage of production. Those are perfect examples of where IR spectroscopy as a quality testing method really, really shines. Anytime you can run the sample on IR and keep that material off of your column and not burn through solvents and hard consumables is great. And ultimately, that's going to lead you to a more efficient and cost-effective quality testing program.
Awesome. Okay, and we have another question here. Are there other sample matrices that the IR technology can be applied to?
Certainly, yeah. Out of the gates, a great example would be fish meal, related material product, both pre and post oil extraction. And we have placed portable units on fishing vessels that process their catch right on the boat, and they're monitoring protein, moisture, fat in real time with IR rather than waiting till they get back to port. In a more general sense, IR is a great match for any organic material. So whether we're talking about animal proteins, grains and seeds, oils, food products, or food ingredients, IR is a really powerful tool that can provide data for multiple parameters in a single test cycle, making it a really efficient testing solution to have as part of a quality program.
Perfect. Thank you so much. All right. Well, I just want to, extend a thank you to everyone who joined us for today's presentation. And Anthony, thank you so much for, walking through all of these different topics. Please reach out with any additional questions, and we would be happy to connect further. This now will conclude today's presentation. I hope everyone has a wonderful day.